All right. We're going to start. So today we will continue defining the scope of the field of quantum transport and reviewing some of the basic concepts, a couple of basic concepts from solid state physics. What I would like to start with is defining various relevant energy scales. Yeah? So the next slide, I've summarized them all like that, but this one is kind of important, so we will spend the whole slide on this one by itself. So charging energy is an energy associated with adding a single electron to an isolated island. And this is a prototypical example for many experiments in the field of quantum transport. In particular, all those examples where we're talking about quantum dots, so zero-dimensional quantum systems where electrons, particles are confined in all three dimensions. And the only way to get onto such a quantum dot is via a tunneling process from a lead or something like that, or maybe by being excited by a photon. So these kind of examples all deal with charging energy. And so charging energy is E squared over 2c. Yeah, that's the charging energy associated with a single electron. And what you need to know always is the capacitance of the system. And capacitance of the system can be comprised of couplings of this isolated island to the nearby conductors. In a real device, there would be source and drain contacts, some gate electrodes nearby, and you would have to know the capacitance to all those elements. But likely you can also measure this capacitance. We will talk about this later when we discuss Coulomb blockade. But in a very simplistic example, where if you just have a sphere and you're wondering what would be the capacitance of that sphere, you probably all remember from basic physics that the capacitance of a sphere is roughly proportional to the size of the sphere. I have to include the dielectric constants, but basically this is a good rule of thumb, way to estimate the capacitance of a system if you simply know its size. Yeah, and once again, this is only if you neglect couplings to nearby metals. If you have metals nearby, conductors, that all these estimates can be thrown out the window. But in outer space, this would be the capacitance. And if it's not a sphere, but some strange shape or rectangle, still roughly the dimension of the system would give you the right capacitance. And what I want to draw attention primarily to is here in this table they have calculated the capacitances and energies for different size spheres, ranging from a fairly large sphere for quantum transport and for nanoscale, so 10 microns, that is almost macroscopic, and all the way down to, in this case, 10 nanometers, 0.01 micron. And the capacitances go from femtofarads to, is it atto? What is 10 to the minus 12? Pico. Yeah, exactly. So from femto to atto. Yeah, so that's the scale. Yeah. So the capacitors you would have that you could solder with your hands, those are picofarads and nanofarads. And these are the corresponding charging energies, and in this case they're normalized by temperature. And that is also a very good conversion to have in your mind. What is the temperature scale correspond to in terms of energy? So a good rule of thumb is that 1 Kelvin is 100 microvolts, microelectron volts. So to be more precise, it is, I think, 86 microvolts. If you take kBt and convert it into energy, divided by the electron charge, you would get something like 86 microvolts. A rule of thumb is 100 microvolts. And so going from 10 microns to 10 nanometers, you see that the capacitive energy, so energy to add one electron to the island, goes from sub-degree Kelvin scale to very hot scale. And these indicate the method you need to reach this temperature. So you have to use a helium-free refrigerator, just put it in liquid helium, liquid nitrogen, and you have to actually heat it up to overwhelm this energy scale. And so that a comparison between charging energy and temperature is very useful, because it also tells you at what temperature you will see charging effects from adding single electrons to such islands. So if you take a very small island, 10 nanometers, charging effects will be very, very strong. Yeah.
So this is telling you what temperature you would get spontaneous charging, not when you're actually applying external voltages?
Yes, that's one way to look at it. Or like I just said, at what temperature would you not see a difference between an electron being there or not? Yeah? At what temperature the single electron charging effects are relevant? And so if we talk about nanostructures, so are we down here, then pretty much below 100 degrees Kelvin, charging effects from single electrons become relevant. Okay, so we discussed already two energy scales and the relation between them, and so we touched on the thermal energy scale, and down here we have the charging energy in this table. We also even indirectly touched upon this second one, the EV energy scale. This energy you can give electron within your experiment. By applying a voltage from a battery, you can create a potential difference between source and a drain in your device, or on the left and the right sides of your resistor, and all the electrons in the system, you can think of them as having this energy. So even at strictly zero temperature, you can still overcome the effects of any other energy scale, the charging energy, the quantized conductance energy, or magnetic field energy, by just simply giving electron the energy at your will with a bias. Yeah? So this is the energy that you're free to give. And how much energy are you supposed to give? Well, if you want to add an electron to a system, it is very convenient, like in thermodynamics, often in solid-state physics, to talk about the chemical potential. Yeah? So we will refer to chemical potential as an energy required to add another particle to the system. So if we are dominated by Coulomb energy, by charging energy, then that would be the chemical potential that you have to pay. Yeah? But we might also be dominated by something else. For example, if we apply a very large magnetic field, it could be that the chemical potential is determined by Zeeman energy if our particles have spin. So that's where this one comes in. Now, this one is very important. Electrons are fermions, and so if it's not a confined box where we have to talk about quantized levels, then electrons, for example, in your source lead, where you have billions or Avogadro number of electrons, would occupy all states up to the Fermi energy, right? Everyone knows that, right? Who doesn't know the Fermi energy? Okay, so the Fermi energy is the energy that the electrons have in the source or in the drain of a nanoscale device. And it is also important to realize that only electrons around the Fermi energy are important. Yeah? So the ones below, all those states are occupied, and so primarily electrons that take part in transport are at the Fermi energy. And so very often in many examples, if you're wondering what velocity do electrons have or what momentum do they have, well, they simply have Fermi velocity and the Fermi momentum. Yeah? So that's a default answer. Now, of course, there are exceptions from this. For example, if you apply a bias and you create a difference in potential between a source and a drain, then the electrons in the bias window become relevant, because on the drain side all these states are available because it's lower, and on the source side all these states, so Fermi plus bias, are occupied, so they will all want to go across. Yeah? So by adjusting the bias you can make more and more electrons relevant to transport. And this energy is a purely quantum energy, and it comes from confinement in a box. Yeah? So for a sphere that I showed as an example here, you could also ask what would be the energy of a particle if this were a quantum mechanical box. Yeah? And that energy would be somehow proportional to the dimension of the box as well, yeah? In the appropriate power, depending on the dimensionality of the box. It would be proportional to the square root of the size of the box or the size of the box, etc. And so you could be in a situation where it is not clear which one of these two energy scales is dominating, and you would have to do an explicit calculation. So for example, if the island, the quantum dot, becomes very, very small, then it could be that the quantum confinement energy, the quantum energy, becomes larger eventually than the charging energy. Yeah? So that, but if the box is sort of micron sized, then probably you are dominated by just the charging energy. Okay. And this last energy scale is maybe the least trivial of all to understand. It does come in quite often in quantum transport and in mesoscopic systems, so systems between nano and macro. It's called the Thouless energy after Thouless, who first introduced this energy scale. And the simplest way to understand this energy scale is if you take the time that the electron spends inside a quantum conductor. Yeah? So if you have a piece of metal or a cavity or an island, there is always a time when electron enters, and then it spends some dwell time inside this island, and then it leaves. And so if you take an inverse of that time multiplied by h bar, that would be the Thouless energy. Yeah? So one simple way to understand the relevance of Thouless energy is by, for example, comparing it to dephasing time. Or dephasing, if we say that Thouless energy is equivalent to some kind of a dwell time, we can compare it to dephasing time. And so if the electron spends inside the conductor a time which is shorter than the dephasing time, then the entire process of coming into the conductor and leaving the conductor will be completely coherent. Yeah? So the phase coherence will be maintained. And so quantum mechanical effects will play a major role in such a process. But if the dephasing time is much shorter, and that means that the Thouless energy is fairly low, in that case the transport will be less quantum and more semi-classical. Okay. So this is a kitchen sink of energy scales, but I think it sort of outlines the important processes that can be happening in a quantum system. So let me draw a sketch where I will try to use most of these things in one picture to illustrate how they come in graphically. So we will use an island, and the island will be coupled to a source and a drain, and these will be very close together, and there will be another piece of metal farther away, and that one is called a gate. So okay, first of all, in the source and in the drain I can define chemical potentials, and they don't have to be equal. For example, a chemical potential here, now this is also the energy scale. I can draw it here, and the chemical potential on the drain can be lower. So this will be a source chemical potential, and this will be the drain chemical potential. And the difference between them, that will be the, which one? This one, the bias. Yeah? So where does this bias come from? Well, how can I create this bias difference? Yeah, from an external battery, right? Somewhere out there, source and a drain are connected to a battery. On one side we maybe put a ground, and in between there is a battery. Okay. Now, KT, this energy scale, it if we now plot the occupation of electrons around this chemical potential, what KT does is it will create a little bit of electrons above the chemical potential and some empty spaces below. It will smear this distribution, and it will become a Fermi Dirac distribution at finite temperature in the source, and same in the drain. Yeah, so that means there'll be some electrons with an energy higher than this chemical potential that I just defined, and there'll be some empty states below the chemical potential. Now, if I want to know the Fermi energy, I would have to ask myself whether it's a source or a drain, but it will be either around here or around here. Now, we have to go onto the island for talking about all the rest of these. Yeah? So first of all, a charging energy, well, this island would have some capacitance, and this capacitance will be its self-capacitance, and that's what's calculated here, the self-capacitance. But it will be influenced by the nearby source, drain, and the gate. Yeah? So it will be some capacitance of the island. And that would give me the this energy scale. Now, the size of the island will give me some quantization of levels inside the island, because this is a particles that are on the island are confined, so we have to solve the Schrödinger equation for a particle in a box. And finally, the Zeeman energy, well, maybe some of these levels are spinful, and in that case, in magnetic field, they will split in pairs of levels depending on spin. Yeah? And finally, if I want to know the Thouless energy, I would have to know basically the strength of these tunnel barriers and the dwell time inside the dots. So I have to calculate the time it takes to tunnel onto this, how many times does a quasi-classical electron have to bounce back and forth before it can escape, and how long does it take to escape. So if I add these rates, I can calculate the tau-less energy for this system. Okay, now we talked about energy scales. Now we will talk about length scales, and some of these are the same concepts, but for some of these it's much more convenient to think about lengths. Yeah? And we already touched upon the most important one of all is the wavelength of a particle. We touched on it in the first lecture, but here it is given in a little bit more detail what that is. So as I said already many times, for quantum transport we have to consider electrons as waves, and so interesting effects come from the wave nature of electrons in a conductor, so specifically the quantum mechanical effects, and those effects are first and foremost are determined by the wavelength compared to the size of the whatever system we're talking about. Yeah? If you want to know the wavelength, well, your best guess is to just take the Fermi wavelength of a particle in a certain material. And so for metals, we all know very well what the wavelength is, right? It is roughly the distance between atoms, maybe a little bit longer. Why is that? Well, because remember, you have to go into the reciprocal space, right, into K space, and every lattice site contributes a single electron to the system, and the level to which K space gets occupied is determined by the number of sites. But the distance between sites, which is the inverse of a quantum of momentum in K space, the distance between sites is the inverse of a quantum of momentum in K space. Yeah? So then it's very easy to see that the Fermi wavelength is about the same as the distance between atoms. Maybe a factor of pi here and there comes in. So that means in metals, for the density of electrons, which is very large, we would get a Fermi wavelength of some nanometers. Yeah, so very short. And that means that in order to see quantum effects, we have to work with systems which are nanoscale size. So here's one example of such a system. It is a surface of a metal. The metal is copper. And what they did here is they picked individual atoms of iron and they put them on the surface. See, you can see how they constructed it. Picked them up and aligned them one by one to form a perfect sphere on the surface of iron. So every single dot here is a single atom. The way they arranged the atoms is by picking them up with a STM tip and moving them around. Yeah. So with a charged tip under applied voltage, they manipulated the atoms, and then they took a picture. And what this scanning tunneling microscope gives you is a density of electronic states as a function of space. Yeah? So this density of electronic states form the perfect ripples, these kind of rings, when the quantum corral was enclosed completely. Yeah? So what this is, it is an interference pattern of electrons that fly on the surface of copper, and they interfere with this corral. And the period of this interference is something like the wavelength. So you can see that the wavelength here is comparable to the spacing between atoms in a metal. In semiconductors, we are, you could say, a bit more lucky, because in these materials like silicon or gallium arsenide, nominally these materials are semiconducting. This means that at 0 temperature there are no conducting electrons. Yeah? And then what we have a freedom to do is to add some dopant atoms into these materials and populate the conduction band a little bit to a much lower density than in metals. Yeah? So then every 1,000th atom maybe contributes a conducting electron, or maybe even less. So then for such a low density, the wavelength of each electron, which is roughly the volume one electron occupies in K space, right? That is much lower, higher. So the wavelength can become tens of nanometers. Yeah? So then a much larger structure will behave quantum mechanically. The second important energy scale has to do with the fact that real systems, be it metals or semiconductors, are not perfect. They're not perfect lattices. And they have some defects. Defects could come from the surface, or they could be some misarrangements of atoms inside the lattice, or in the case of semiconductors, I just told you that electrons are induced by doping, so by introducing other atoms into the semiconductor. Could be silicon atoms in gallium arsenide would contribute charge carriers. And then the imperfect arrangement of those dopants would create a certain degree of disorder. No? So first of all, if we did have a completely perfect infinite crystal, right, what would happen? So imagine you have electrons living on a completely perfect lattice. Who remembers from solid state physics what would happen if an electron has a certain momentum? Maybe we apply a small electric field, a voltage bias.
Standing waves?
Yeah, kind of. So there will be actually there will be something called Bloch oscillations happening, right? So without any scattering, electron will just be accelerating indefinitely, but what will be increasing is a K momentum, not a real momentum. So then the electron's real momentum will be oscillating back and forth in the Brillouin zone. And actually, if you apply voltage to a perfect crystal, instead of a DC current flowing, like in a resistor, you would get a AC current, and you would might even get radiation coming out, because electrons will be oscillating back and forth, and that's called Bloch oscillations. Now that behavior is extremely hard to get. People actually try to exploit this to create sources of radiation, right? It would be really amazing if you just take a perfect crystal, you apply a voltage, and then based on how much voltage you apply, you get radiation of a completely tunable frequency, and hopefully high fidelity, so very narrow spectrum line. But that doesn't work, and that's because it is very hard to create perfect crystals. Yeah? So that's the point. The behavior is very bizarre for perfect crystals, but most things we deal with are imperfect. And then, of course, it is very natural to define. Yeah?
Can they get it in graphene?
Graphene is really not so perfect. And so the biggest problem with graphene is that you put a layer of single atoms on the surface, and the first thing that happens is it ripples. So it becomes a little bit wrinkly. And also what matters is what is underneath graphene. So if you suspend it in vacuum, it is better. But if it's lying on some surface, it's really not so clean. You do much better still with gallium arsenide than you do with graphene. But you can maybe try to see these Bloch oscillations in something like graphene, but maybe you will see one oscillation, not very many. Okay, so disorder is important, and these are the sources of disorder. The ones I mentioned so far are static. Yeah? So imperfections in the lattice, disorder in dopant positions contribute to maybe surface, roughness on the surface. there are also dynamic sources of disorder. And those come from interactions between electrons that disturbs the Bloch oscillations. Already that disturbs them. And then, of course, also phonons. So the fact that the atoms are not fixed in their positions, but they can also move. So you have phonons, and the spectrum of phonons through electron-phonon interaction couples to electron waves and makes them scatter. So before we before we are able to define the proper length scale associated with scattering, so some kind of a distance between scattering events, we have to also consider different kinds of scattering. And they basically fall into categories like elastic scattering and inelastic scattering. And the difference is, when we say elastic, we mean that a scattering process happens without electrons changing its energy. And inelastic means that it exchanges energy with something. And you can already see that scattering off of imperfections of a lattice is most often elastic. That's because a lattice site, an atom, is much heavier than an electron. And so that if you scatter off a very heavy object like a wall, you don't change your kinetic energy. And so those are elastic scattering events. And then still you can have a more and less dramatic scattering event based on whether your momentum has completely reversed. So maybe if you hit head-on an atom, or if you hit it on a side, sort of, then maybe your momentum just changed a little bit. And then people distinguish between large angle scattering and small angle scattering. And inelastic processes are those where you interact with kind of equals. So if you scatter off a phonon, you could give your energy to the phonon, or you could absorb a phonon into the electron in a quantum language, and then your energy would change. So that is shown by seeing that the initial momentum, this arrow length, is shorter than the final. So the length of the arrow has increased. Same with electron-electron interactions. When electrons of equal mass but maybe slightly different energy interact, they can exchange energy. So this is described here. Then, of course, especially the inelastic scattering is strongly temperature dependent, and that's because the strength of electron-electron and electron-phonon interaction is determined by temperature. For phonons, it's especially easy to see because just the density of phonons, their population changes with temperature. If you lower the temperature, phonons freeze out, and that's easy to understand. The lattice becomes less vibrating, so that's then the inelastic scattering time might actually increase. Okay, so now it is natural to determine this energy scale called mean free path, and that's a distance between collisions, roughly, and the precise definition is it's a distance an electron has to travel before its momentum is randomized. So before any correlation between the initial momentum and the final momentum is lost. And you can already see that even for the two types of elastic scattering, a mean free path would mean very different things. For elastic scattering with large angle, mean free path is simply a distance between the two of such scattering events, because after just one event the momentum is completely randomized. But if you're dealing with small angle scattering, you could undergo 10, 100 of these events, and still there'll be some correlation. Roughly the momentum will be pointing in this direction. It will just diffuse around this point, and so it will be a much longer distance before it's completely randomized. And so actually this type of scattering is very important in high quality semiconductors like gallium arsenide two-dimensional electron gases, probably also in graphene, for example. Yeah, so the mean free path is determined by when is the momentum randomized. Yeah, and it's also sometimes called momentum relaxation length.
So does it mean that in the like nanowire system or low dimensional system, if you reduce the dimensions, you can increase the mean free path?
Sometimes you can, and sometimes you can't. Yeah. So actually, the naive first reaction would be to say that if you artificially confine your structure, so it were a bulk three-dimensional structure, and then you made it into a nanowire, my guess would be that you have reduced the mean free path, because you've put a surface which is a scattering center very close to the electron. Yeah? So in principle, crossing the nanowire once along the diameter might be enough to randomize the momentum. Unless this scattering of the surface is of a specular nature. Yeah? So if between these lines is the confinement and the electron makes a perfect specular reflection, then I could say, well, these scattering events, even though the momentum flips after each event, they're really not randomizing the motion. Yeah? This momentum, for example, I could just ask, when does this momentum get randomized? Yeah? And so when you scatter very perfectly, when the surface is a very high quality, so no things sticking out from letters, but really a flat line, and you undergo such a process, then the momentum along the wire will not be randomized for a long time. And this is actually the case in real nanowires. So you have to scatter several times off the surface before you randomize. So it is not a priori possible to say what will happen if you go from bulk to confined structure. Okay. Now, remember I told you that your best guess is to say that the electrons travel at Fermi velocity, and so then you can also define tau, which is a momentum relaxation time. Yeah, so the time between scattering events. And in a sense, the time scale is even more fundamental than the length scale. So for example, the time scale, if you know this time, you can, in a classical system, define this important quantity, which is called the mobility. We will come back to this formula in the next lecture, but you can also calculate the diffusion constant for electrons, and that's all clear, right? So if you know the scattering time or scattering length, you can calculate the diffusion of electrons in 2 dimensions, 3 dimensions, whatever system you have. And then I already mentioned to you that the mean free path, if you just define it as a momentum relaxation time, that refers to the direction of momentum, and that is called the elastic mean free path. And you can also associate an inelastic mean free path with processes like this, when you exchange energy with something. And the importance of this length scale for quantum transport is also very, very high, because if you think of an electron as a wave, a quantum mechanical wave propagating, and now all of a sudden this wave has changed its energy. Maybe it lost energy to a phonon. The first thing that happens is that for sure the phase of that wave got completely scrambled. So if you think about a dephasing length, a length after which you lost the phase of a wave, for sure it is limited at the upper level by the inelastic scattering length. So that also tells you that interacting with other electrons or with phonons will limit the quantum mechanical nature of transport through any system. And this is where we come to this dephasing, dephasing length and dephasing time. So like I just said, this is a key concept for determining whether transport is quantum or classical, because in principle, so here's the wavelength of an electron, but electron can travel over numerous wavelengths and its phase can still evolve coherently, right? So like in the example of a quantum corral, here the system is several wavelengths in size, and what we see is an interference pattern which period is determined by the wavelength, but the coherence is preserved over the entire picture here. Yeah? So that is the difference between wavelength and dephasing time. So this is a time or a length after which the initial phase of the wave is scrambled, yeah? So that there's no correlation between the initial phase and the final phase. And by performing essentially interference measurements on electrons, there is a particular kind called weak localization that we will touch upon later. You can extract the dephasing length or the dephasing time for a given system. And so this was measured in many works, but here's one example from this paper in 1907, where they studied gold, thin gold wires. So what they show is that the dephasing time increases as you lower the temperature. Here's the temperature, goes down, and the dephasing time increases. And that, one simple reason why that could be is because of what I just said. The dephasing processes are limited at the upper scale by inelastic scattering, yeah? by giving away energy to photons, phonons, and well, also photons and other electrons, and those processes freeze out at lower temperatures, so the phase coherence of a system increases. That is rather universal to many quantum systems. Yeah? So a very good number for dephasing time at low temperatures is something like 1 to 10 nanoseconds. Yeah? So that is a good ballpark number. Below a few hundred millikelvin, the dephasing time will be some nanoseconds. And then if you know the mean free path of your system, or the diffusion length, the diffusion constant of the diffusion constant of your system, you could calculate the dephasing length, so the relevant length scale over which the wave remembers its phase. Yeah? And then you can ask yourself, well, is my cluster, is my quantum object longer than the dephasing length or shorter than the dephasing length? So in the example that I specifically drew with a small island, most likely the dephasing length is longer than this island. Yeah? But if I drew a very large open cavity, this would be an open question, whether it is fully phase coherent or not. And we already looked at this example in the first lecture. This is Aronoff-Bohm oscillations, and they originate from interference of electrons with themselves, right? So electrons come from the source, and now I don't have such a simple island like I drew there in between source and a drain, but I have a complicated multiply connected geometry, a ring, and electrons can roughly follow this side of the ring or this side of the ring. And then we apply magnetic field this way, and based on how much flux threads this ring, we get a constructive interference at the drain or destructive interference. Yeah? And those are the Aronoff-Bohm oscillations that are associated with that process. So for this very clean system, the dephasing length is very large. At low temperatures it's many microns, and therefore we're able to see these oscillations with very high contrast, very high quality. But if we were to make this ring bigger and bigger and bigger, and finally when we exceed the dephasing length in size, the oscillations will be washed out. They will no longer be observed, and that's because a wave coming in here and traveling here will have, well, by the time it gets here, no phase correlation with the wave that was traveling along this branch. Okay. We will in this course we will look at many different materials, low-dimensional, bulk materials, metals, semiconductors, sometimes even single molecules, and so they will have very different quality and very different properties, but roughly we can quantify transport just from the trajectory point of view. If we think about electrons as semi-classical balls into these classes, determined by how much disorder there is in the system compared to the size of the system. So if the trajectories are diffusive like this, there is a lot of scattering inside the system, then this is diffusive transport, and it is governed by the Boltzmann equation and the Einstein relation and the Drude formula, right? In the classical transport limit. But we will also work with some systems where a mean free path of an electron is many microns. I once worked with a two-dimensional electron gas where electrons could travel without scattering for 25 microns. That is a very, very long mean free path. And since I already told you about large angle scattering and small angle scattering, most of that was small angle scattering. So electron was not actually traveling in a straight line for 25 microns and then scattering. It was most likely going in little kinks, and then finally after 25 microns it was clearly going in a different direction. So those are the details. But there are very ballistic systems out there, and one of the following lectures will be devoted to ballistic transport because it gives rise to many beautiful effects. When you can shoot electrons very far in your conductor, you can observe interesting phenomena. And okay, in between you have quasi-ballistic transport. That's when there are maybe a couple of scattering events in your system. So sometimes in nanowires, where you have confined a couple of directions, but electrons can still scatter a few times before they leave the nanowire. That would be quasi-ballistic, for example. So this table now summarizes all the length scales that we discussed. And we started by summarizing all the energy scales, and now the length scales. And you will see that you can kind of draw a graph. If I give you a conducting material, you could ask yourself, first of all, is it diffusive or is it ballistic? Yeah, meaning, are there many scattering events inside the material, or do electrons just cross it in one go? And then, is the transport classical or is the transport quantum? Yeah? And you can have all four possibilities. And they are distinguished by the ratio of the length scales that we just discussed. So let's go one by one. In the classical case, this is a case of a resistor. For example, so a very conventional piece of metal, maybe at room temperature, a microscopic size. What we have is a Fermi wavelength is very small, a nanometer. Inelastic rate at room temperature, inelastic length would be also comparable, few nanometers. And momentum relaxation, well, if it's not a pure piece of gold, but it's some alloy, maybe a copper-nickel alloy, then every other atom is an impurity, and so again, elastic length scale will also be some nanometers. So all of these are 1 nanometer, and the size of the system is a millimeter. That's a classical regime. Now we can make it quantum by one of 2 ways. Yeah, so these two are still small because we keep the same material, for example, copper nickel. So this one is a nanometer and this one is a nanometer. But what if we shrink it to a wire which is 1 nanometer wide? Yeah? Then we might see some quantum effects. Or what if we lower the temperature, such as the inelastic rate, interactions with phonons and with other electrons go way down? Well, we might also enter a quantum regime, even in a larger conductor, but much more clearly when both of these conditions are satisfied. Now, on the ballistic side, it is very similar, except now the size of the system, for example, can be still much larger than the Fermi wavelength, but now the scattering time, the elastic and the inelastic, that has to be larger than the system size. Yeah? So remember this picture. Yeah? There is no scattering in the system size. So this is capital L, and this would be LE and LI. And to make it quantum, we have to make the wavelength, or now the dephasing time, comparable to the size of the system. Yeah. So this would be a device like this. This cartoon shows a semiconductor with some gate electrodes that define this island. An electron is a wave because the dephasing length is very long, and it interacts with this structure and comes out on the other side. But we can also compare these 4 length scales to other length scales in the system. For example, we can define kind of the charging length scale, or remember, capacitance is roughly proportional to the size of the system. Yeah? So we can ask ourselves whether for a given classical conductor, charging effects are important. Single electron charging. Well, if this condition is satisfied, for example, then single electron charging is not important. But if charging energy is larger, for example, by making the system smaller, then charging effects might become important. Some effects, especially in magnetic field, you can see a change in transport if you fit a small number of wavelengths or orbital periods inside the conductor. There are certain size effects which, based on how many orbitals fit inside the conductor, you can see the resistance go up and down. So then size geometry of the sample will influence the transport. And the same on the quantum side. So this table, I believe, is from the review by Beenakker and Van Houten, which I gave you a reference for in the last lecture. You can see it on the archive. And when I was a grad student and a postdoc, I used to just print this out and put it in front of my computer. I think I'm going to do the same here. I just didn't get around to it. But I find this extremely useful because it has all these quantities that we discussed today and their interrelationships, like from the simple ones, like how is the Fermi energy related to Fermi momentum, but then scattering time, diffusion constant, resistivity. If you say know the resistivity from your measurement, how can you extract the mobility and the density, etc., etc. So this is just a recommendation. If you need to navigate all these different length scales and energy scales, just go to Beenakker and look at this table. And it also gives characteristic values for 2 of the important semiconductors. For example, the effective mass for gallium arsenide, it is very low. This is in the units of the electron mass in the free space. Yeah, so the effective mass of gallium arsenide is very low, and in silicon is quite a bit higher for electrons. Okay. Now we have about 20 minutes left, and I would like to switch gears a bit. I think it was you know, a long laundry list of length scales and energy scales. They are very important, and we will come back to them many times again. So I appreciate you patiently listening through this whole list. And now, for fun, I think we have time to look at some data and also make a very important point that this field, quantum transport, is all about interpreting current voltage characteristics of interesting devices. Yeah? So, because the only thing we are allowed to measure is pass a current and measure voltage, or apply voltage and measure current. And current voltage characteristics, it's very natural that they will contain all the information from which we can deduce the interesting quantum effects. And of course, for most conductors, current voltage characteristics are extremely boring. They are straight line, determined by the Ohm's law. And we will try to stay away from those. We'll try to go to the fringes where current voltage characteristics look interesting. So here are two examples. Actually, you can obtain both of these in the same device, even though they look, if you think about it, they look very different. Though shape-wise, it just looks like you've rotated it, but a very different meaning, because now the x's are current and voltage. And this flat part is somehow flipped. So this is a current voltage characteristic of a typical so-called Josephson junction. And it's a device where you took two superconducting metals and brought them very close together, leaving a tiny, tiny gap of an insulator. A dielectric could in principle be vacuum, could be nothing, or could be some dielectric material. And inside the superconductor, what is the most striking characteristic of a superconductor? Who can tell me? Why is it called a superconductor? Let me rephrase. It has zero resistance. Yeah? So what will happen if you apply a current to this superconductor? No. There will be no voltage. Yeah, zero resistance. Yeah? Then, of course, this is only valid to a certain degree. You cannot apply an infinite current. At some point, you exceed the critical current. And this is what this current voltage characteristic shows you, that in this case, this is a current biased measurement. That means we have an ideal source of current, and we can gradually increase the current. As we increase the current, no voltage develops and until we reach the critical current, and then we see this sudden jump to a finite voltage. And then actually, if you look here, this looks like a straight line. Now we've entered the Ohm's law. Yeah? So if you extrapolate it, it goes to zero. So this is a normal state resistance, so-called. Yeah. So the amazing thing is that now I told you that this is not a piece of superconductor. It's two pieces of superconductor separated by nothing, or for sure by a non-superconductor. And still, we can have current without any voltage. So that means that this zero resistance state, it somehow jumped from one piece of superconductor to the other. And so the particles, the Cooper pairs that carry supercurrent, they are able to tunnel. They are pairs of electrons. They're able to tunnel across this tunneling barrier and maintain this superconducting coherence over the non-superconducting section. And when you see something like this in your data, especially for the first time, you can be very excited. You are clearly not measuring an Ohm's law. Similar and different. So in a sense that there will be a critical current, they are similar. But in the details, like the shape of this cusp, whether there is a hysteresis here or not, those are very different. And there is a book this thick written just about the different current voltage characteristics of various superconducting geometries. Yeah, so in principle, if you in your lab measure a current voltage characteristic of some kind of a superconducting device, with some probability you can open this book and compare the current voltage characteristic, but you have to pay attention to various small details, like are there little steps here, or is this a sharp switch or is it rounded, and is there a small slope here or not? Well, I've seen your data, so I'm just pointing out all the things that, that you see. But you know, if you pay attention to all these details, you can tell the difference. And for sure, this insulator has a consequence of making this critical current way much lower. Yeah? It is not like superconductivity just ignores it. It costs you something to tunnel over this barrier. And if you keep increasing this gap, eventually this supercurrent will go to zero. Now, this is actually, this could be the same device, but we are doing here a different measurement. We are applying not a current bias, but a voltage bias. And what we see here, well, technically we should also see a little spike here from this supercurrent effect. But other than that, we see that we keep increasing the voltage and there is no current flowing. So completely opposite behavior. Yeah, this could be infinite resistance now, and the resistance is infinite. And that is related to the fact that there is, again, this tunneling barrier. And so to overcome a tunneling barrier, it requires a certain voltage. I will not go into more details of this because the story deserves a separate lecture in principle, and I might actually do that. But I just wanted you to kind of stare with me at this data and appreciate how different this is from Ohm's law. So in fact, from this voltage you can read out the energy scale associated with the superconductivity in this structure. So if you multiply this by charge, EV would give you the superconducting energy gap. Okay, and then I wanted to show you a much more rich data, and these are now not fictitious, these are from real devices. And first let's look at the left side. This is a so-called quantum point contact. I will have a separate lecture on these devices exclusively, and I already mentioned them once. But basically these are one-dimensional constrictions through which electrons can propagate without any scattering, like pure, very clean waves. Yeah? And then conductance in these structures is quantized in the units of the quantum of conductance, E squared over h. Who can guess what this factor 2 comes from in the quantum of conductance? No? Spin, that's right. Yeah. So this is you can even see it here. At zero magnetic field, these kind of dark areas are these conductance quantization plateaus, and they occur at 2e squared over h, 4e squared over h, etc. And at very large magnetic field, many Tesla, now you have them at half, 1, 1.5, 2. And now I will explain what these curves are. Now this is these are, each line is a current voltage characteristic yeah, an IV curve, except what is plotted on this axis is a derivative, yeah, conductance. So it's a dI/dV. So this is still a voltage bias across the quantum point contact. So it is just like this voltage bias here. So we apply a difference between source and a drain. Yeah? And we plot not the current, but the derivative of current with respect to this voltage bias. And this kind of representation of the data is often called a waterfall plot. Yeah? The data flows like water. And you can, sometimes in this representation, you can see features that you otherwise don't see. And what is interesting about this data is that the curves don't have any offsets. The data really does this as a function of some parameter. The parameter in this case is the width of the quantum point contact. And so we change the size of the quantum point contact, and as we shrink the size, the IV curves, they fall down like water. And now what do you see here? Well, the dense areas, that means that we keep changing we keep shrinking the quantum point contact, but the conductance does not change. So in particular here around zero bias, you see this dense region, and against this dense region, those would be conductance plateaus. Yeah? So I keep shrinking the quantum point contact, but the conductance remains the same quantized value. Yeah? So the way I shrink them is, of course, by using voltages on the gates, by squeezing with electric fields on the electrons. But so just by plotting data like this, I can say, aha, conductance shows quantization. Yeah? I can also see many other interesting things which people were confused and maybe still confused about for many years now. For example, here at low bias, there is a little peak in conductance, some kind of a zero bias conductance peak. Yeah? So there are many papers written just about this peak. What is it from? Maybe it's an effect of interactions between different electrons. But for now, we don't need to think about this, but just appreciate the fact that when you look at the current voltage characteristics, you can, just with your eyes, see various features. You don't even have to do any calculations. You can just stare at the data. This is another beautiful example of a transport experiment. And so the trace here, that is another current voltage characteristic. It looks like a mess, and probably no one would be able to explain every little bump in this dependence to you. But what can you say about this curve that strikes you, for example, in comparison to these graphs? Yes. These are almost perfectly symmetric with respect to zero bias. Yeah? These are almost perfectly symmetric. And this one, somehow, it's not symmetric. And so sending electrons one way, so applying a bias like that, is not the same as applying a bias like that. It's unimaginable in a resistor, for example, right? Or even in a quantum object like this. This is still symmetric. Yeah? So here, some kind of a symmetry is broken. And the thing that breaks this symmetry, it happens to be spin. Yeah? So what they're measuring here is it's called a double quantum dot. It is a more complicated structure than I drawn here, because there is one of these islands and next to it another one, like that. So one well, another well, and a source and a drain. Yeah? And what happens inside these wells, these two quantum dots, is that electrons there are tuned such that the levels are spinful. Yeah? And so what is important is, what are the spins of the electrons that are sitting on these islands? So for example, suppose on the farther island, close to the drain, we have a spin-up electron. Then if another spin-up electron comes into this island, then the two of them are having spins in the same direction. Actually, that means the transport is stuck, because two electrons of the same spin are not allowed in the same small space. This is a Pauli exclusion principle. Two particles with the same quantum numbers cannot occupy the same quantum level. So this electron is not allowed to go to this level because both have the same spin. And the higher level, where it's allowed to go, is way far out of reach for this bias. So if we give it more energy, it will go. And this is what happens here. Finally, the current is allowed. That's because we applied more bias and we reached a higher level. But here, this transport is blocked because of this triplet state forming. Now let's look from the other side. If we reverse the bias, then here we had the bias this way, here the bias is this way. Well, in that case, actually it doesn't matter what the spin states are, because of the following reason. So suppose here you still have the spin up electron like here. Then, okay, so then from the drain lead, spin up electrons cannot enter, but there are plenty of spin down electrons. And so those spin down electrons will just keep flowing through the system. So this is called spin blockade. It is only working in one bias direction, and it breaks the symmetry of this IV curve, and this effect was observed many times, but remarkably for the first time it has been observed from such an ugly looking asymmetric current voltage characteristic. So this is a beautiful example of where current voltage characteristics are important. And I personally really like this effect, the spin blockade. So depending on the spin state of the system, electrons can flow or they can be also blocked. And this effect is not just beautiful, but it is also very useful. It is a principle behind the operation of single spin qubits in quantum dots. So we will go into the details of that later in the course. Right, so I think the time is up. There's one question I can answer, otherwise we are dismissed. And next week I'm away, so the 2 lectures will be cancelled. I should be able to send all of you an email today or tomorrow with some references and how to do the homework.